Now, this week, we don't have actually really any slides for you guys because we're pretty much just going to spend today going over a guided project. And first of all, just thank you all for coming out. I know it's the week of Thanksgiving, but we appreciate you taking the time. So as always, we have the beginner cluster or the beginner track asset cluster linked up here. Go ahead, check it out. You'll see that we have the link for both the skeleton code and the solution. So, if you want to follow along and write the code with us, make a copy of the skeleton code. And then we also have the solutions up there for, your future reference if, your code isn't running or you're trying to do this again sometime later. So with that being said, let's see. I'm going to give you all, 30 seconds to open up the asset cluster and get into the skeleton and make yourself a copy. And yeah. Okay. All right. So first of all, show of hands, who was here last week and or is kind of up to date in like how to use modules and other libraries? We're all there. All right, beautiful. Because we're going to be referring back somewhat to what we went over last week. We're sort of assuming that you have at least a tiny bit of an idea of what you're doing. If not, feel free to ask questions. But hopefully, you guys remember at least like what NumPy is and stuff like that. So to kick things all off, as we are pretty much always going to do, we're going to be importing a couple of key modules to our notebook. Pretty much the standard of we have pandas, NumPy, and then matplotlib, just so we have something that lets us plot stuff. So to get started, the first thing that we're going to do is implement f of x, right? So f of x, you can see up here, is equal to pi x plus 10, a relatively simple function. So given some x, we're going to multiply it by 10 and add 10, or multiply it by pi and add 10, and that's going to be the result of this line. So how would we go about implementing this? This is going to be one line of code real quick. Any thoughts? You don't have to tell me exactly how you do it, but just like throw something out there for me. Is that a hand? Was that not a hand or? Yeah. Yeah, implementing the function. np.pi times x plus 10. All right, awesome. Very close. You pretty much have all of it. Return. There you go, right? We want to actually return the value because if we don't, it's just going to multiply x by pi and add 10, and then that value is going to disappear into the ether, right? So we'll run it, and as you can see, we have it all implemented. So now the next thing we're going to be doing is generating 100 data points in the range of -5 to 5. And this is going to be how we're going to roughly approximate a line, right? Because, we're going to be dealing with some discrete data points instead of, one continuous line. So does anyone remember from last week how we would go about doing that? Nobody? Well, does anyone remember how we'd go about just generating some data points, right? Some like, yes. Yes, right? So we can use linspace, and so np.linspace. And then how would we go about doing exactly what we are trying to do here, which is generate 100 points between -5 and 5. Any ideas? I'll give you guys a hint. When you put the parentheses up there, a lot of times, a lot of IDEs and notebooks will tell you like, what the different parameters you're expected to pass in are. So looking up there, can anyone tell me what the first parameter we're going to be passing in is? Well, what's -5? Yes, right. And why would we pass in -5?
That's not bound.
Yeah, exactly. Right. That's where we're going to be starting. We're going to be starting at a balance of, or a value of -5. And then for the next one, hopefully you guys can figure this one out without the help of the suggestions from the notebook. What would be the next parameter that we would want to pass in? 5, right? Because we are going in a range from negative, starting at -5 and ending at 5, right? Now, finally, we want to specify the number of data points, right? And it does say we want 100 data points, but to make it a little bit more computer sciencey, right? We want to ideally be storing 100 in a variable. So what should our next and final parameter be? N, right? Because n is equal to 100. And so now if we decide we want, I don't know, 10,000 data points instead of 100, we can do it relatively easily. So now if we run this, actually, I'll put that there. Run this, you can see that does indeed look like an array of 100 data points between -5 and 5. So, all right, any questions so far? Hopefully not. This should hopefully all be a review from what we covered last week. All righty. So now what we're going to do is, is initialize the weight and bias randomly. Essentially, what we're saying, right, is we're trying to learn the function pi x plus 10, right? But because we know it's pi and 10, we can't like just start at pi and 10. We have to be like, okay, we're just going to act like we have zero idea what this function is. And so we're just going to give it 2 random values. And from those random values, we're going to figure out what value we should actually have, right? That makes sense to everybody? I got 1 nod. All right, multiple nods. I'm going to say that's a yes. So now we're going to be implementing y hat, which is up here, right? This is a generalized form that is saying that, if you remember, like, y is equal to mx plus b. Here we're doing y is equal to wx plus b, slightly different, but, basically the same thing. How would we do this? Refer back to our initial function up here. How might we do this? No ideas. If we look at the previous function that we just implemented, what did we do to do pi x plus 10? Oh, come on, we just told you guys. What did we do to implement pi x plus 10?
I think it's like just write like a multiplication function plus an addition. So you have to determine like your equation.
Yeah, exactly. Right? You're just returning the equation itself. So here, what we can do is return w times x plus b, right? And what that is saying is now, instead of it being, pi times x plus 10, we want to make this a general form that can support any weight and any bias. And so we're going to be like, we're going to do, like whatever the weight is times x plus whatever the bias is. So any questions so far? Okay, beautiful. So next up, we have this line right here. Can anyone tell me what this is doing? No ideas. Well, can anyone tell me what reshape does? No guesses as to what reshape does. Yeah, right. So if you remember last week when we were dealing with NumPy arrays, we were talking about how, if you have a one-dimensional array, right, its shape is going to be something like, 100 comma, right, where it's basically, you just have a bunch of elements. So it's not really a matrix. It's just like an array that is 100 elements long, right? But sometimes it is very helpful for us to have this in like a more general matrix form. And so you can transform it. And one of the more common ways that we're going to transform it is into a shape of something like 100, because then this is going to say that this is going to be a matrix with one row that is 100 values long, right? So if we run the code up here, you'll notice that it's pretty much the exact same array from before, except instead of 1 bracket, we have 2. And that's because instead of one long array, it is now like a matrix that we can do linear algebra and stuff on. So, all right, I'm going to assume that you guys got all that because I'm not seeing any questions. And so now we are going to do y is equal to f of x, y dot shape. This is just saying, okay, for each one of these x values, we're going to run it through our function, right? All right, I'm just gonna go and then we'll take periodic breaks for questions. But right now, it doesn't seem you guys have. It seems you guys are getting this perfectly. So, why hat is not returned. Oh, do not run my hat. That's my bad. So, all right. Let's take a look up here. So we have first modeled our x and y, right? And y, so x and y, this line is going to be our actual function. You know, this is going to be the y is equal to pi x plus 10 function that we're trying to model, right? But the y hat function, we're passing in 0, 0, and basically saying that, hey, we're going to be, if we don't know the weight and bias, and we just say it's like 0 and 0, or we can also replace it with the w and b from up here, what would that look like, right? And so can anyone tell me which one is our actual function that we wrote earlier, the blue or the orange? Blue, right? And how do you know that? Yes, right. So there's a number of ways you can look at it, but probably the most prominent to me is that the blue one has a slope that seems to be, at least eyeballing it, roughly around 3, which is right. 3 is basically pi. And if you look at the 0, you can see that at 0 it seems to be right about at 10, which is not something you can say for the orange line, right? So any questions about that? Yes.
So for the scaffold one, you work with the y and y. Sure, why would you replace 2 zeros in the first two coordinates to w and b? You just get a no slope line.
Yeah, I mean it doesn't really matter if I'm doing 0 or w and b, right? Because up here we initialize w and b to some random value between 0 and 1. So it's going to be pretty obviously like distinct. And so the real point here is just us saying that right now, we have no idea what the hell w and b are, and we're going to be working through this to figure out what it actually is, right? But very good question. Anything else? All righty, so you guys are nailing this. Beautiful. So now we're going to implement mean squared error in 1 to 2 lines, right? So it's just a little refresher for you guys. Mean squared error is we're going to sum up each data point. And so yi is the, So yi is the actual value. And then y hat I is our predicted value. And then we're squaring that difference and then dividing it by n. So, the squared, so the error is just the difference between what it actually is and what we predicted it to be. The squared error is squaring that, and then the mean is just we're taking the average of it. Does anyone know how we're going to go about doing that? Well, let's break this down into parts, right? First of all, let's get the error. So if I write error is equal to anyone want to help me here? That seems pretty good to me, right? Y minus y hat. Okay, so we have the error. Now, is that all we need to do? No, right? We need to do the mean squared error. So we have the error, but we don't have the mean or the square. Anyone have any ideas how we might go about getting, the mean or the squared part? Even simpler. How would we get the squared error? I've decided I don't want the squared error. I don't want the error, I want the squared error. How could we modify this line to make it so that we are no longer getting the error, but the squared error?
Close that in parentheses, double multiply by 2.
Beautiful, right? So enclose that in parentheses, double multiply by 2. we're basically saying we're going to get the error between y and y hat, and then double multiply by 2 in case, actually, I'm not sure if we covered this, but if you multiply by 2 like this is going to multiply every value by 2. But if you put 2 multiplication signs, that means it's to the power of that. So you can do like, if you want to cube it, you can do that. If you want to, I don't know, if you want to do like the square root, you can do that. But right now, we're just going to do that. Okay, so we're very close, right? We have the squared error. Now, all we need is make it the mean squared error. How would we do that? Okay, yeah. So say we're trying to get the mean squared error. So we can do mp.sum on this entire thing, on part of this thing. Entire thing. Yeah, right. We're not just going to be summing up y. We're going to be summing up all of these different components. So we have that. And so are we done? Can we just return this value? No. What are we missing?
There's like 1 over the total number of how many.
Yes, right. So what we have right here is the sum squared error. We want the mean squared error. So there's 2 ways we can do this. As you pointed out, we can divide it by the length of the array, which is one approach. But there might be NumPy has a built-in function to do sums. Do we think that it might have a built-in function to do averages? Yes? No? Yes? You have 50-50 chance of getting it right. Yes or no? Yes, right? Okay. Oh, woo, wow. You guys blow me away. There is, in fact, a way that we can average stuff, which is mp.average. So now, if we change our function up to look like this, I'm just changing it from mean squared error to loss, so that way we're returning the loss. And we run it, hopefully should run good. And now we have implemented our mean squared error. Any questions about that? All right, beautiful. Man, you guys are nailing this. So, all right, so now we're going to be doing some dot products. Well, we're going to be going over mp dot dot. So is everyone here familiar with how matrix multiplication works? Well, or not even familiar, but you guys remember when we talked about this, right? All right, I'm going to take that as a yes. If you have questions, ask me as I'm going through. So anyway, so we're just going to define real quick an array or a matrix that is one row. In that row, it's 1, 2, and 3. And so that means, and then we're going to set C equal to A. The shape of A is 1, 3, again, because it's one row with 3 values or 3 columns, right? Does that make sense to everyone? Now, I have a bonus question. Now, I had a little line right here. Who can tell me what A dot T is going to do? Yes. Move it from 1 to 2?
So like the original HA, it would multiply 1 to 3. But would it change to 2 and 3?
So, okay, so you're saying that if we call the dot T, if we do A dot T, it's going to change it from a 1x3 matrix to a 2x3 matrix? Interesting hypothesis. I'm not quite sure if it's 100% right. Does anyone have any other ideas, guesses? Transpose? And what does that mean? Rotate, right? So yeah, so that's a little bit more accurate than, we're not necessarily adding, just a whole nother row out of nowhere. Instead, what we're doing is we're basically saying, okay, for each row, we're turning it into a column, right? So in our case, A has one row, which is 1, 2, 3, and now it only has, and it has 3 columns, right? Now, what we're going to have is 3 rows and 1 column because we've rotated it 90 degrees. So now instead of 1, 2, 3, it is instead of 1, 2, 3 in one row, it's 1, 2, 3 in one column. That makes sense to everybody? Okay, I'm taking that as a yes. Now, one last question to test your understanding. What would A dot shape or what would A dot T dot shape output? 3, 1, right? Why? 3 rows in one column. Beautiful, man. You guys are nailing this. So, yes. Now we're gonna run np dot dot, and what np dot dot is going to do is it is going to perform a dot product on these two matrices. More specifically, we're basically just doing matrix multiplication because we're dotting the row and the column from matrix multiplication. Does everyone understand perfectly how what's happening here? Why we have 14? No, that's totally okay. That's what I was hoping for. Actually, I was pretty sure that no one else is brave enough. You guys all okay? Well, still, just for a little bit of a refresher, right? The way matrix multiplication works in linear algebra is you take some matrix like this, right? You have 1, 2, 3, 1, 2, 3, and the key insight is that this guy has the same number of columns as this guy has rows. So if this is a 1 by 3 matrix and this is a 3 by 1 matrix, you can see that this guy has 3 columns and this guy has 3 rows, which means they're valid to be multiplied against each other. And then what we do is for each row in the original matrix, we multiply each value in that row by its corresponding value in the corresponding column. So what does that mean? Here in our first row, we are going to multiply each value by the value that corresponds to it in this matrix or in this column right here, because this is the first column. So if we go through and do that, we would get what's the dot product, which if you guys have done any work with vectors, you'll remember as being you're just taking the components, multiplying them together and adding them. And hopefully you can see how this is exactly what we're doing here, where we're multiplying together, the 1 and the 2 and the 3, and then adding them all together. So this is going to output to us 1 times 1 plus 2 times 2 plus 3 times 3. So 1 plus 4 plus 9, which is going to be equal to 14. And then finally, this is all inside of some final matrix, which is going to have the same number of rows as the first one and the same number of columns as the second one. So in our case, this would be a 1 by 1 matrix. This is mapping from like different spaces. I think I said this last week, but if you want a much more elegant explanation of what's actually happening here, 3 by 1 round has a great video. I would highly recommend. But does that basically make sense to all of us? Yes. All right. So now we all get why we got 14. Beautiful. Beautiful. Now we're doing A dot T instead of C dot T. So this is going to look a lot more like, this is going to look like 1, 2, 3 times, or no, not that big. 1, 2, 3. So this should probably just give us the exact same answer, right? No, why not?
So first thing I think you're doing with 1 by 3, and then this be 3 by 1, so 3n. So you're ending up with 3 by 3.
Beautiful, right? So first major difference, this is a 3 by 1 matrix and this is a 1 by 3 matrix. So it is a valid operation because they both have, there's one column in this guy and one row in this guy. But as we talked about, this is going to output to us a 3x3 matrix, right? So now, why don't we really quick walk through this? So if you remember, for each row, we are going to be dotting it with the corresponding column as it goes through. So who here can tell me what this is going to output? Well, let's start with the first one. So the first row and the first column are being dotted together. That is, and so if we take this guy and we dot it with this guy, which in our case, because there's one value in each, just means multiplying them together, what are we going to get? 1, right? All righty. So now sticking on this row, we're going to say, okay, so that was the first row, this was the value that was in the first row in the first column. Now we want the value at the first row in the second column, which is going to be this dotted with this, which is 2. Is that what I heard? Beautiful. And then finally, the last value in the row is going to be 3, right? And then, so now if we go to the next row, it's going to be these two dotted together, which is?
Well, like the 3 would be 2, 4, and 6.
2, 4, and 6. There you go. And then finally, 3, 6, 9. Beautiful. So, and as you can see, at row 1 and column 1, it corresponds to row 1 and column 1 dotted together, and row 1, column 2 corresponds with row 1, column 2 dotted right here, and so on and so forth. Any questions about how we got that? No? All right, beautiful. You guys have basically mastered linear algebra. You don't need to take 33A or B. So yeah, so as you can see here, it's exactly the result that we predicted. Now, finally, does anyone remember what A times C is going to output? I'll give you a hint. It's not the same thing as the dot. Does anyone remember how NumPy arrays act when you multiply them together? Yes? Exactly, right? It pretty much behaves as like a deconstructed dot product, where instead of summing it all up, it just stays in place, right? You have 1, 2, 3, and then 1, 2, 3. So you're going to do 1 times 1, 2 times 2, 3 times 3. So it does it element wise. So wonderful. Master all these operations. Any questions about any of all that? All righty, no questions. Beautiful. So next, what we're going to be doing is implementing our gradients with respect to W and B, right? So we have the two gradients here. Do we have any questions about them? This should hopefully be review from when we covered, I forget what week, but this should hopefully be review from prior workshops, and you can go find an in-depth explanation there, but hopefully we're all have some idea of what a gradient is, and we're okay with, even if we can't completely remember the derivation right now, just accepting that this is the gradient, and you can go look at that in more detail later. That work for everybody? All right, wonderful. So we want to return our gradients from this function gradients, appropriately named. So the way that we did this in like the solution is we made it so we had the gradients value is a dictionary where dw corresponds to the derivative or the gradient with respect to w, the weight, and then gradients b is equal to the derivative with respect to the bias. So we pretty much just have to fill in the gradient with respect to w and the gradient with respect to b in these two spots. So actually, does everyone know how dictionaries work in Python? Does anyone not know how dictionaries work in Python? We all have a perfect understanding. I'm happy to talk about it for a little bit because I realize we haven't talked about it. All righty, we all have experience with Python. Beautiful. So first of all, we're going to be implementing the gradient with respect to W. How would we go about doing this?
NP dot average y hat minus y times x times 2.
Yes. Yes, absolutely. We are not averaging NP dot average in the solution. I'm not entirely sure why that would be, but I guess we're showing off. No, we're using some. Okay, well, okay, yeah, no, exactly. We can they dot it. So we can both dot this. Well, they're just showing off that you can dot. Oh, yeah. Doesn't, sorry. So yeah, right. You can do exactly that. Pretty much, as you hopefully have noticed, this up here is just the average of the error times the x value times 2, right? And so probably something like just 2 times NP dot average y minus y hat times x. So, all right, beautiful. And then for our gradient with respect to b, how would we go about implementing it? Any guesses?
Basically the same thing as the W definition, but A goes into X.
Beautiful, right? Does everyone understand why we can? It's pretty much just the exact same thing except no x. We're all good on that. All righty, beautiful. So, yeah, and then one thing. So if you're looking at the skeleton code, there is one thing that I do want to point out that might be a little bit confusing, which is the way that they actually execute their gradient with respect to the weight W is slightly different. It looks like 2 over n times np dot minus y. So that might be somewhat confusing. So I'll break it down even further and say that this is equal to 2 over n times np dot sum of y hat minus y times x. And can anyone tell me why? This is a little bit more advanced. So well, I suppose one way to start is probably treat it like an equality, because there's the 2 over n term here. We can just say that essentially np dot dot of y hat minus y, the transpose of x, and np dot sum of y hat minus y times x are both going to be the same. Does anyone know why? Any guesses? Yes.
So it's very much ambiguous. It depends on like how is it implemented, but I guess like.
So I suppose I should probably give that to you guys. Or actually it's y minus y hat. No, don't listen to me. I messed that up down here. So I suppose I should probably tell you guys that the way it's going to behave is we are going to get essentially for y, y hat, and x, they're all going to be 1 by n matrices of their respective values, right? So for x, for example, it's for us, n is 100, right? So x would be like, I don't know, -5 all the way to 5 inside of this big old matrix, you know, y and y hat would be something similar. So each value in y and y hat would correspond. So at like 0, you know, our y would be equal to 10. So with that in mind, what exactly are we doing up here with the dot? Any ideas? Well, let's walk through this. So we understand how the dot function actually works, even if we're not entirely sure what we're trying to do here. We all understand how it works, right? So, okay, so first of all, we have a y hat minus y term. So, okay, for each value, we're getting the error, right? So we can be like, I don't know, E1, E2, all the way to En. In our case, n is 100, right? So y hat minus y is just going to be the error for all of these different values. Does that make sense to everyone? So now what is x dot t going to look like? So what does transpose do? Just talked about it. Any guesses? Flips it, right? It turns it 90 degrees. And x usually is also of the same size, but doing xt would flip it on its head. So it would be a really big vector or matrix looking like this, -5, 5, all the way down. That part makes sense to everyone? So now, finally, we're calling np dot dot, which is just going to do matrix multiplication between the two of these. So what is the dimension? What are the dimensions of these two vectors? What's the dimension of this? 1 times n, right? Because we have 1 row and n columns. And over here, what's the dimension of this? N times 1, right? So we can see the n's match, so we are allowed to do multiplication. But more interestingly, what is the dimension of the final matrix going to be? 1 by 1. So it's just going to be one value inside of here. And that is very useful. And so does anyone now have any guesses as to what this is doing here? Like what the np dot dot is going to be doing? So can anyone explain? Basically, what I'm asking is, can anyone explain to me why np dot dot is going to be the same as np dot sum? Yes? Yeah, no, go for it.
Because after you do the matrix multiplication, you have to end up adding all this together to get one value. So you're going to be adding the same amount. And then if you were to multiply every error by x and just adding them together, it's the same math.
Beautiful, nailed it. Hit the nail on the head. No, so that is exactly right. These are all of our x values. And so if you think about it, if you take this error and we multiply it by the appropriate x value, then this becomes a matrix where it's just a matrix that if we sum all of the values, it's going to tell us what the sum of all of the error is. Well, not all of the error, what the sum of all of the gradients are, right? And so that's essentially what we're doing here, right? The x value for one, the first x value is going to correspond to the first. The second is going to correspond to the second, so on and so forth, until we get to the nth x value, which is going to correspond there. And then finally, the way it's going to work is we're just going to add it all up. So it's just a roundabout way of adding all of these things up. Does that make sense to everybody? Yes.
Would it occur such that the dot product returns like a matrix of 1 by 1, while dot sum returns like a scalar, like a...
Yes. So dot sum would return a scalar. The dot function is going to be returning a 1 by 1 matrix. But you know, for our purposes, we're just gonna ignore that part. You know, they are technically a little bit different. You know, but you know, for our understanding, we really don't need to. You know, it's not super important. And great question though. Any other questions?
we also need to divide the whole thing by n.
Yes, yeah. I just took out the 2 over n.
We use some average for TW.
Yeah. You absolutely can, right? Essentially, what I've done is gone through like 3 ways of doing it. Just because on the skeleton code we do it in this way, which I didn't want to confuse anyone if they're looking at it in the future. But great question. Anything else? No, alrighty. So now, if we want run the gradients function, we can see that we are going to be getting a value of negative 53 about for our gradient for with respect to the weight, and a value of negative 18 for our gradient with respect to the bias. So now we're going to be training our model, right? So if you remember, the idea behind our gradient descent is we're going to be taking the gradient at each spot to figure out how we need to adjust our weight and our bias. And then we're going to adjust it that way. And then at the next spot, we're going to adjust it again. And our goal is to get it to a point where the loss is 0. Does that make sense to everyone? So now what we're going to be doing is updating or implementing our actual function here, right? So the first thing that we have to do is, so you can see that we're setting alpha equal to the learning rate, right? Because alpha is the learning rate. And the first thing we're going to do is get the actual predicted values, which, how do we get the values that we're predicting? Well, so what are we using to predict the values? Are we using pi and 10? Are we using pi and 10 to predict the values? No. Exactly, right? We're trying to figure out what pi, well, we know it's pi and 10, but we're trying to figure out what those values are. So we're making our predictions based off of our weight and our bias. And what function did we write a little bit earlier that is going to let us do that? Y hat. Beautiful, right? So we're going to do y hat and then weight bias x, right? So that's just going to say, give us your predictions based off the weight, the bias, and the x value. Now we're going to be computing the gradients, right? Which, hint, hint, we just wrote a function for up here. So what would we do to get the gradients down here? So we just wrote a function that returns our gradients to us. So what are we probably going to do to get the gradients?
Just put the function in the variable.
Yeah, we're going to, well, we're technically not putting the function in the variable. We're going to invoke the function, put what it returns in the variable. So we're going to do something like gradients, and then that, and then are we done here, or is there anything else we need to add to this line? Yeah, right. The parameters that we were passing in were the x, the y, and the y hat, except for us, where did we store the y hat? Predictions, right? Beautiful. So now I'm just going to go ahead, because it's a dictionary, we can just pull the values out and do right? Because if you remember, that's how we formatted it up here. And then finally, how are we going to update W and B? I'll give you guys a hint. It's right up here. What do we need to do to update W and B? Yeah, right. And do we do that for W or B with the gradient? Which Do we use the gradient of W for W or B? Or both? Just for W, right? And why not B? That has a different gradient, right? The gradient for W doesn't really tell us anything. Also, the way that we're going to be passing in B and W is going to be inside of an array. So instead of just doing B minus equal alpha times DB, we're going to do B0 and just index it. So don't worry too much about that. So, alrighty, and then now we're finally going to be returning W, B, and losses. And as you can see down here, the loss, we're just making use of the function that we wrote earlier, the mean squared error, and then we're just saving the loss on our list of losses. So, any questions? No questions? All right, beautiful. So, finally, we're just going to go ahead and run W, B, and losses, or run gradient descent on W and B. So how do we do this? We're just calling the function. No guesses? All right, okay, I guess I'll give you guys a break. It's just, we can do WB losses. This is unpacking the return value. You don't have to worry about it too much. And then we're just going to say is going to be equal to gradient descent xy w b. And then it says we have decided we're going to be using 0.03 as our learning rate. So here we're going to do this. Does this line make sense to everybody? Yes, no, maybe so. Or blank stares, that works fine too. Okay, yeah, so we're basically just running the function that we just made. And as you can see, we got pretty close, right? What our original weight and bias were pi and 10, right? And what does it say our weight, its prediction for our weight and bias are? Yeah, it's really close to pi, really close to 10. So great job, everyone. Give yourselves a pat on the back. You've just done linear regression. Woo! And so finally, what we're going to do is we're going to plot, and you can see now it's very close. It's pretty much the exact same line for our predicted line and our actual line, right? It's not at all like up here where it's pretty much just a straight line. And then finally, the losses we can plot, and you can see it looks something like this. So what this is telling us is that we start off, we have a really high loss because our model is really crappy. Like it's just random weights, right? But it really quickly is able to be like, this is the direction I need to be going. So it improves really quickly. And then as it gets closer and closer, the gradients are going to get smaller and smaller because it's closer and closer to being accurate. So you see your losses go out and sort of, begin to plateau towards the very end. So any questions? No questions. All right. Wonderful, 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 wonderful. So we want to invite you all to experiment with different learning rates other than the ones that we've provided. So if we just go ahead and run it here with a smaller learning rate, you can see that this is the difference in the loss for large learning rate, medium learning rate, and small learning rate, right? As you can see, I don't know what that should be negative. We'll chase that down later. But as you can see, the difference between a small, a medium, and a large learning rate, because where did I put? Okay, I don't think that should be negative. You know what? don't worry about it. All right. But so as you can see, right, with a small learning rate, our loss does not go down nearly as quickly as a large learning rate does or a medium learning rate does. It's a little messed up. I don't know if the losses should be negative like that. We're not going to worry about it. But essentially, the behavior that you're going to observe is that hopefully all of your models are going to eventually approach the correct values. But it's a matter of picking what's a good learning rate, right? If you choose a really tiny learning rate, you're going to be making really small changes. So it's going to take much longer for you to get there. But if you choose a really big learning rate, you're going to be making really big changes. And that can lead to instability, where essentially, it's sort of like, you're trying to park your car perfectly, like parallel parking, and like you're not a very good driver. So you keep like slamming on the gas and like overshooting back and forth, back and forth, back and forth. So ideally you want to be in some sort of middle ground. But any questions about that? No? All right, beautiful. Beautiful. Let's see. Okay, I am going to hurry up because we are pressed for time. So now we're going to apply this on a real data set, right? We knew it was pi, we knew it was 10, but now we want to do this on something where we don't necessarily know what it is. So what we're going to do is we are going to load in a data set where we are essentially, we have the SAT score and the GPA for the person who got that SAT score, right? And you can see here, we have a bunch of fancy stuff about like what the minimum value is, what the standard deviation is, what the bottom 25th percentile is, what the maximum score is, all sorts of stuff, right? And we want to see, we're like, okay, in general, if you have a higher GPA, we might expect to see, somewhat of a correlation between your GPA and what your SAT score is, but it's not going to be a perfect line. And so it's up to us to figure out how to fit a line to that data. So what we're going to do is we're first going to put the SAT and GPA data each into their own arrays, right? Because you can sort of think about it as it being the X and the Y. We don't want the X and the Y together. We want one X and like one Y, or in our case, we want one SAT and one GPA, right? So what we're going to do is we're just going to transform it into an array on data SAT. Now, last week, did we get time to do pandas last week?
Yeah, they covered a few.
Cover a little bit of pandas. Okay. This, I don't know if you guys remember, but when you load data in using pandas, you can access the columns using this notation, very similar to a dictionary. But so essentially, we're saying, give me the SAT column, and I'm going to turn that into a NumPy array. And wouldn't you know it, it's pretty much the exact same thing for the GPA. So now we're going to run this, and here we just have some code that we wrote to plot it. So you can see, okay, so there's a rough relationship. You can see that we have somewhat of a trend, right? With like, if I were to look at this, I'd be like, the line probably is something like this, like a general slight upward trend. But getting an exact line is going to be a little bit difficult. So now what we're going to do is we are going to reshape the SAT data and the GPA data. So first, I'm just going to get the number of values by doing SAT.shape 0. The SAT and GPA should be the same length, right? Because for each data point, we have both an SAT and a GPA. And so if I call shape and I get 0, that should tell me how long it is. And this is because if you remember, if we have like 100 values in just an array like that, it'll have a shape of like 100 comma, but we want to do most of our stuff with like matrices. So we're going to try and reshape it so it's a matrix with one row and like 100 columns. And so in that case, but doesn't really matter too much. But what we're going to do here is we are going to say, let's say the SAT is going to be our X data, right? And we want to reshape it from whatever n is. Right now, its shape is something like n comma, and we want to turn it into something like 1 comma n for its shape. So how could we go about doing that? Beautiful. Well, it's in this case, because we already have a NumPy array, we're calling the shape method on itself. A little pedantic, but yeah, exactly right. NumPy gives us a built-in method that lets us reshape the arrays and matrices. So what we can just do is SAT.reshape 1, n, right? Because that's the shape that we want it to be in. We're like, screw this. I don't want your lame non-matrix version of the data. I want the matrix version. And Y is probably going to be pretty similar. Does anyone want to tell me what we should do here? We want to reshape it the exact same way, right? Beautiful. You guys are killing it, killing it, killing it, killing it. So yeah, you can see n is evidently 84, which you also could have noticed up here. The count is 84. And we have the shape being done correctly. Now we're going to initialize W and B to some random value. I could ask you guys, but we didn't spend too much time on it. I'm just going to pull it from up here because we already did this once. Where is it? Here it is. So we're just going to call NumPy's random function to give us a random value. So now we're going to be running linear regression using the gradient descent function. And it says here, picking an optimal learning rate is key. So, this is something that really a lot of times just requires experimentation. But there are like some ways that we can think about it. For example, our data here, right? We can look at it and we can observe that it doesn't have like a strong increase. Like our slope is probably not going to be huge because, if you think about it, between like, if we are plotting like from here to here, it's like, as we have increased the SAT score from 1600 to 2000. So like by 400, we've gone up by like, I don't know, maybe like 0.3 in GPA on like average. And so that's going to be a very small slope. So that might be one thing that could tip you off to that fact that we might want to have a very small learning rate, right? Another thing is that the intercept here is going to be very small, like the intercept probably is going to be, it's not going to be like 200 or something. It's going to be most likely in the range of likely GPAs, which we would expect to see. So with that in mind, we probably want a very small learning rate. Do we have any guesses for, or not even guesses, any like suggestions for what we might want to do? The learning rate? I mean, I'm just saying, just give me like a number. Like this isn't like a right or wrong thing.
2.6.
2 points. So you want to do a learning rate that's much higher than it was before. So we can do 2.6, but I will warn you, right? Remember what we talked about with a large learning rate sort of jumping all over the place. That is not great behavior. And so doing 2.6, which up here, right, to hone in on it, we had a learning rate of 0.03. So that would be, let's see, what, like about 90 times as big for a data set, which, as we discussed, is going to be using much smaller values. Might not be the greatest idea. Anyone else have any other guesses? Or if you have a guess that's like maybe a little smaller?
I think it would be like very small, maybe around 0.2.
0.2. So again, that is higher than our learning rate before, which, as we discussed, was for a data set with much larger values. So I'll just say that our suggested learning rate here is very, very small. It is X, Y. Call it W2, B2 instead of W and B. X, Y, W2. So that is point is 0.705. So that's a really tiny number, right? That's way smaller than we were before. But again, as we talked about, the value for the weight and bias are going to be much less here than it was in our hypothetical data set. So it kind of does make sense that we would want to pick a value so small. Does that make sense to everybody? So if we run this, you can see that we got a value of about a weight of about 0.0013, and then 0.86-ish, and one thing to note is that as the random value changes, we're hopefully going to converge relatively nearby, right? Like, okay, see how like this changed a little bit? Like this is now like 0.78-ish, and this is like 0.0013 instead of 0.0015. So we're not going to always converge to the exact same value, but hopefully what we want to see is that when we change the weights, we still are roughly in the same neighborhood, right? So now, I guess they already have it here. Okay, I think the code is already filled in. But now we can see that this is our line, right? It's telling us that the line that we fit was about here, and that looks about right. There's no perfect correlation, so it's not like a perfectly straight line of the data, but that seems to about match the general trend. Any questions? All right, you guys got this? I would recommend you guys poke around, see what happens if you increase the learning rate a lot. See what happens if you even decrease it even further. Like how does this behave? Stuff like that. And then finally we can plot the loss, and as you can see, the loss is able to plummet down. Now I'm going to hand it on over to Eric for a quick little going over of logistic regression.
Hey folks. No, we just covered a lot of content. So before I cover some more content, we're going to be we dove a lot into a bunch of concepts. We're going to actually be working with formulas, applying everything in a second. But you want to hear a fun fact or something that I just found out today? I just found out that turns out y'all know Dance Moms, the show, right? Turns out the kids who danced on the show, some of them go here. So there was what I was freaking out. Naya Sue Frazier from Dance Moms goes here. That's crazy. Anyways, logistic regression. So I know we're a bit short on time. We're going to get out on time, so I'm going to sort of shimmy on with things if that's all right. But no, I'm just thinking Dance Moms goes here, that's what. Okay, logistic regression. So remember that the idea with logistic regression, right? We can have models that can linearize data, right? Where if we're trying to work with house prices, we're trying to get a model that can predict house prices. But not all models are for that. Some models like to categorize information. So for instance, if I were to input photos of cats and dogs into a model, maybe I want a model to predict, okay, these images are dogs, these images are cats, right? And the mathematical notation of, I guess, of dividing up input into two different categories is logistic regression. And so in terms of doing that right here, we have a little lab set up. So we're going to import our modules. We're going to set a random seed. So we're just going to randomize our data right here. And then we're going to create our data here. There's a bunch of stuff here. But essentially, when you look at our data right now, we've color coded it for y'all so that y'all can see it more clearly. But essentially, as of now, our data is two different, you can categorize into two different classes. And the idea with logistic regression is when you want to create a model that can sort of draw a line that divides our data in half, where one side is one class, the other side is the other class. So in this case, this would be splitting in between blue and orange. So in terms of doing that, first things first, we need to, let's just print out the shape of X and Y. These are what they are. But if we want to split our training data and our testing data, we can actually do this in one line here. So let me do that here. Crazy thing about libraries, they design these so that it makes it really easy to program like these like models and stuff. So if you want to split your training data, you will follow this notation right here. So we're going to pass in 4 inputs here. Variables that can store our training data for our class X, and variables that can store our data, our training and testing data for our class Y. So that's what these 4 variables are here. And then we imported this lovely little library here. So if we want to create and split our training and testing data, we'll just call this single method here called train test split. Crazy, right? And what we'll input here is our class X, so X, our class Y. We're going to input this parameter called test size here. And all this is saying right here is, given our data sets of X and Y, we want to only utilize 20% of that data as our testing data. And the rest of them is going to be our training data. So our training data is going to be like what we use to like see if our model's actually working correctly or not. And then we're also going to utilize this other parameter here, which seemingly makes no sense. But in terms of if you want to create a model that can output the same data every time, let's say like I'm writing documentation or something, if I'm working with a lot of random values, obviously I want to try and have a model that can output the same like data or the same outputs, regardless of how random it is. So all this random state is equal to 42 is saying is it'll randomize exactly the same every single time, no matter how many times you run it. So it's not necessarily random, it's like controlled randomness, if that's fair enough. We chilling on that? Cool. So before we dive into the actual model, we do have this last little blurb here on how classes work in Python. Oh, that's crazy. Well, they already completed the lab on, oh, that's crazy. On the skeleton code, it's already complete. But essentially the idea, is everyone here familiar with like object-oriented Python? Yeah, no, yeah, maybe. All good. Essentially the idea with classes in Python, we will define an object defined as so. We initialize an object, and then we can give these objects, I guess, like variables. So in this case, the object that we're working with will have a B variable and it'll have an H variable. And then each object can have their own methods that can work with its own variables. So for instance, like we can define an area method here to work with this B variable and work with this H variable to find the area of, I'm assuming this is a square or a rectangle here. So similarly, if I wanted to find the parameter, I would just like find 2 times the base, 2 times the height. I would add them together. You can do that all locally in Python using classes. Is that cool? All right. Anyways, I don't know if y'all have like scrolled through, like did a little skim of this little workshop here, but you probably got to this part right here and you're just like, whoa, 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 right? It's a lot less, I know it looks really intimidating, but what you'll come to learn the more and more you work with like machine learning and AI is the hard part is the concepts, the easy part is the implementation. So right in here, what we're about to do is we're about to apply logistic regression onto a data set. And to apply logistic regression, the general workflow is to go from top to bottom and run each of these formulas. So if we understand what these formulas are doing, and generally these formulas are just applying math, coding it is pretty trivial, as like crazy as that sounds. So because when you look at the actual like formula, it is quite bulky, but when you look at the actual math that is going on, you're just applying like a logarithm to an element, subtract, you pretty much just plug in chug kind of. So I guess TLDR, what I'm trying to say is it looks like a lot, and that's because it is a lot. That kind of sounds like what Gavin Newsom said. But the reality is don't let that scare you at all. Like this is literally just plug and chug. As long as you understand the concepts, you should be smooth sailing. And normally this is the part where like I go like back and forth with everyone, but people are trying to eat dinner, and I respect that. So we're just gonna like go over the general concepts. We're gonna do like a smooth sail through how the code will look, and then we should be good to go. Is that cool with everyone? Wonderful. So essentially the idea, once again with logistic regression, right, is we're given input. We're inputting like input into our model here. And in mathematical notation, we define it using this like function right here, where we're saying that our input is going to be X, and we are going to associate a weight with every single piece of data in our input set X. Whoa, what did I do? Uh-oh. Whatever. It's still on there. So we're going to be working with, once again, this double click. Oh, shit.
Just click outside anywhere. Let's go up.
Yeah,
Go up. Just click the difference. Yeah.
that's crazy. The more you know. Anyways, so all this is saying on a high level conceptual whatever is we are going to be giving input. So our input's X, we associate each piece of data in X with a weight, which tells our model how important this piece of data is in terms of like how it decides things. So for instance, if I have a model that can differentiate images between cats and dogs, I really want to put a lot of weight on actual images of dogs. But maybe if I put like if this input has like an image of a horse, like I want to put a lot, like very little weight, so this doesn't like affect the logic of my model, right? And evidently not all models are going to be perfect, so we add this extra term of a bias to our input. And in theory, like if we apply this correctly into our model, our output will be established in this y hat formula. So conceptually, all this is saying is like, if we give an input, we'll get an output. And this is just, all this is saying is that in mathematical terms, which is quite dense. So in terms of general approaches to how to do that, the general approach is through this loss function right here, which we covered a while back, but does everyone remember it? It's all good if you don't. All right. But generally, the idea with a loss function here, right, is if I give input into my model, how do I know, like, I guess, what is good output? The idea is we throw our input into this loss function right here. So remember that our model, what a logistic regression model is trying to do is given an input, we categorize it into either class A or class B. So in terms of like this cat and dog, like model, like idea, like don't think about it as like class A is dogs, class B is dogs. Maybe think of it as like one model works with I either have a dog image or I don't, and another model works with it as like I either have a cat image or I don't. So all this loss function is saying right here is given an input, all this logarithm is saying is, or that huge bit right there is saying is given a piece of input, we are going to differentiate it into two different classes where it's either 0 or 1. So if I'm 0, I'm in class A. If I'm 1, I'm in class B. And generally 1 means success. So if I'm working with a model that differentiates between like given an image, I can tell whether it's a dog or a not. I would probably associate 1 with I have a dog image and 0 with I do not have a dog image. And all that is saying is that in math terms. So given an input X, or Y in this case, we are going to differentiate it into two different classes. And then all this summation on the left here is saying is we are going to apply this to every single piece of data of our input. Is that fair enough so far? Cool. So given we have this like wonderful, wonderful loss function, right? If this loss function is going to be making our model better, how can we make our loss function better, right? Because if we, in theory, if we have a better loss function, we can get like a better, or we can train our model better. And the way that we can make our loss function better is through these formulas down here. And this is talking regarding gradients of loss and gradient descent. So all gradients of loss is doing is it's trying to minimize the loss function. which in this case means that we're trying to minimize how wrong our loss function is. So that's I mean, it's just a bunch of math, but that's pretty much like what these two formulas are saying right here. And then the idea with gradient descent right here is, given that we can apply these formulas to calculate or to minimize the amount of error that our loss function has, what gradient descent will do is it'll attempt to optimize that minimization. So we can apply gradient descent onto this formula right here, which minimizes how wrong, I guess, our loss function is, in order to try to train our loss function to be less wrong. So that's all this gradient descent is saying. We're just like, we're trying to minimize with gradients of loss, and we're trying to optimize that minimization with gradient descent. That chill with everyone? Cool. So given all these concepts, I know we've talked like concepts today. We're going to begin actually trying to build a logistic regression method. And what you'll come to see is it's pretty much just like translating ideas into math, into code math. So let's go through it right here. There's a bunch of like documentation on like, this is what this is what that is. In this case, you can generally ignore that. But right here, let me catch myself up on here so I'm not giving you all the wrong information here. All right, so first things first, what this huge like logistic regression class is about to do is we're about to establish a model, and then we're going to break it down using logistic regression. So first things first, we need to establish our model. So the way that we're going to do that is we're going to establish our model as a class. So we are going to provide weights and biases to our model. So the way that we do that is with this notation right here. Right? And all this is saying right here is, remember, or I guess I haven't defined this, but X is going to be our notation for our input. So all we're going to say here is we're going to apply a random weight to each of our data points in X. And like I said earlier, with our formula from above, we do need to apply a bias to each of our pieces of data, because evidently our model is not going to be perfect. So the way that we do that, and this little lab right here, is let's define a little silly little local variable called bias. And let's set that to be the random, just like a completely random value in this case, because the point of logistic regression is we're going to try to make it make sense, given a random piece of data in this case. So given that, let's begin trying to break down like what's actually going on here. So implement the sigmoid activation function. So they didn't cover this up in the math part for some reason, but the actual thing that makes the loss function work, remember our loss function is essentially the mathematical way of dividing like input into two different classes. The way that that actually works is through this function called the sigmoid function. And all the sigmoid function is it's essentially like essentially all the sigmoid function is doing in terms of math terms is given a piece of input, you can plot it on a chart where it looks like this, where you have like a curve, and then like you just say like, okay, I'm gonna cut my curve in half. Let's say I cut it in half at 0.5. And let's say if I'm above 0.5, I'm a part of class 1. If I'm below this 0.5 line, I'm in class 0. That is all this sigmoid function is doing. It's essentially just like given an input, it'll give a score in between 0 to 1. If I'm above 0.5, I'm closer to like class 1, or for instance. If I'm below 0.5, I'm closer to class 0. So I kind of lied to y'all with the loss function, but in terms of how we actually implement it, we utilize the sigmoid function. And we've covered this previously. It's pretty much just a plug and chug. All the formula is it's pretty much just an exponential function in the denominator. So in terms of how to implement it, this is how to do it right here. Let me make sure I'm getting this right. So how about let's store let's store our, I guess, categorizations in this variable called activations. And let's literally just word for word, bar for bar, put in our sigmoid function. So this is how you would do it. And in this case, I don't know why they do this in this lab, but they keep switching the notation for our input. In this case, our input's going to be called Z. Who knows why? I don't know. And then we're going to return activations. All right. So you may be wondering like what this like math is right here. Like I said earlier, this is literally what our sigmoid function is. This is the mathematical version of this concept right here. Given an input, I'll give it a score. If the score is closer to 1, then it's a part of one class. If it's closer to 0, it's a part of the other class. And this is going to be the foundational piece of logic that will help our log loss function work as intended. All right. So given that, remember that with a model, there's essentially our models given a piece of, or given some quantity of training data, we're going to see like how right or wrong our model is. So part of that is our model needs to predict, given some input, I guess like a prediction, our model needs to actually do some work so that we can tell whether it's right or wrong. So given that, we're going to implement that down here. And like I said earlier, it's pretty much just plug and chug. So all we're about to do right here is we're about to just implement our hypothesis right here. And remember, our hypothesis is stating if I apply a weight and a bias to every single piece of input, in theory, our model should work in terms of differentiating things between class A and class B. So let's do that right now. So we're going to try to get the output of our model. So let's call this predictions for now, because we don't know if they're right or wrong. And in this case, this will be set to the dot product of our input X and the weights of X. Or whoa, there's a lot of text here. Let me just type this up real quick. So, all right, there we go. All right. So all we're saying right here is exactly that math formula we said earlier. We're going to apply a weight to every single thing in every piece of input in X, and then we're going to also apply a bias because our model evidently is not going to be correct. And then given that, we are going to utilize this method that we've just defined up here, where we're applying our sigmoid function. So let me code it out first, then I'll explain it afterwards. So we're going to apply our sigmoid function into our predictions here. So this would be the notation for that. So all this is saying right here is, first things first, in this line right here, this is our model's logic, right? So given a piece of input, our model is going to apply weights and biases to our input, and it's going to output its predictions. And we're going to store those predictions in this variable predictions. And then in this activate function, this activate method, I guess, is what stores our sigmoid function. So all we're saying right here is we have our predictions stored in this variable predictions. We're going to apply our sigmoid function onto those predictions to score things on a scale of 0 to 1. And I guess like we'll return, I guess, all of those scores. And then from there, what we can do is based on our scores, we can say, okay, if we're closer to 1, then we're class A. If we're closer to 0, we're class B, for instance. Is that making sense so far? Wonderful. Okay, so now that we've defined our sigmoid function, all that fun jazz, it's time to implement our log loss function. This is going to be a pretty big function, and that's because the log loss method right here is pretty big, but it's pretty much just plug and chug. Remember that the log loss is pretty much just breaking down our input into 2 different classes. This is how that looks like in math, and we're literally just going to code that formula bar for bar in code math terms. So this is how that would look like right here. So how about let's store our log loss in a variable called log loss, just to make things less confusing. And we are going to break it down as so. So we're going to take the average. We're going to use the average instead of like applying the sigma sum and multiplying by 1 over n. because it's just easier. And then we're going to apply the nightmare of logarithms that the log loss method is. So this is the way that you would implement that. Oh my God, there's just like so much text. Okay. 1 minus y times np.log. All right. Let me just space this out because that's how I like to code in Python. This may seem like a very long line of code. That's because it is. But this is pretty much just coding exactly what the log loss function is in terms of code math. And then all we'll do for this method is return our log loss. So this is our loss method right here that we can use for later, this entire thing right here. So given that we can apply our sigmoid function to give a score, all this log loss is saying is given a score like in between 0 and 1, I'll say, okay, I have either a 0 or a 1. It just further breaks down our scores. All right. So then after that, we will apply our gradient descent. Again, this is conceptually, it's all the same. It's just we're just applying the actual math into like code math, bar for bar, word for word. So let's do that now right here. So instead of a pass, let's delete that pass. We're about to drop some crazy bars on here. So we're going to establish a formula that is the derivative of our weights. And then we are literally going to bar for bar apply our gradient descent function right here. So this would be the notation for that. We have a dot products. We have a lot of fun things going on. Then we're going to do the same thing with our bias, where we're going to differentiate that, or not differentiate, derive that in a similar fashion. And again, I'm saying this once, I'll say this again. We're literally just bar for bar, word for word, just copying our math formulas and just coding it instead of writing in math terms. All right. So right here, we have just implemented gradient descent, or right here, whoa, not gradient, oh wait, I just coded that in the wrong place. Well, okay. I was thinking like gradient descent is not spelled with 3 letters, so that's kind of weird. There we go. So we have implemented our gradient descent. Whoa, my goodness. My bad. I don't mean to like be scrolling a lot. We've implemented our gradient descent method right here. All this is doing is the exact same math that we've covered before. And then given that, we have so we've applied all of these formulas. We put each formula in a certain method. Now in this fit method right here, we're going to piece it all together. So this is going to be how our model works. This is all the logic right here. Everything we built up through all of these workshops is going to be broken down into 5 lines of code. Crazy, huh? So, okay, first things first, within our model, all this for loop is going to do is it's going to iterate through each of our pieces of data, which in this case is called epochs. So first things first, we are going to create a prediction for that input. So we'll call our predict method that we've just implemented, given an input X. And then from there, we will score it. We'll calculate its loss. So this will give it a score in between 0 and 1. So we will call, oh wait, not grads. We'll call our loss function right here. All right, cool. And then from there, we will try to optimize how well our loss function is doing and also try to better optimize like how well we're predicting things. We will call our gradient descent and we'll store that in these variables. And then from there, oh yeah, then from there, we were talking about training, or not training, what is the notation for it? It's we were talking earlier about a learning rate for our model. We need to apply that now. Maybe a little confusing why we implement it this way, but just trust the process. We are going to, for each weight, apply our learning rate. So in this case, our learning rate is stored in this variable called alpha, and we're just going to multiply that by everything in our weights and everything in our biases. Because again, this for loop is going to be iterating through all of our data. We're going to try to apply our learning rate such that we can go along with it. All right. We're almost there. Don't worry. I know it's getting a little late. But this right here is pretty much our logistic regression model right here. It's just 5 lines of code, given that we've implemented all of these heavy math methods into their own methods. So from there, let's run this piece of code here and pray that it does not fail. It did not fail. Wonderful. So from there, if we run this code, wonderful. Logreg. Interesting. Xtrain is not, oh, did I define Xtrain incorrectly? I may have. That would be quite unfortunate. Let's see. X shape. I swear I thought I did it right. Oh wait, Xtrain. Let me double check something here. Xtrain, Ytrain. Okay, that is really weird. That should be working, but I guess not. All good. All right. Normally I debug this. We're running out of time though, so oh well. I don't think any of these will actually work now, but yeah. Huh. Normally this would be, should I try to wait, Jackson, should I try to debug this or I think it's just a naming thing.
Part of the code that defines Xtrain.
Yeah, like I swear I did. Wait, so let me run that, right? So that runs. And then I'll run this. And then from there.
There we go. Oh, wait.
Logistic regression has more attribute weight.
Oh, attribute weight.
Let's see.
My apologies, y'all. Give us a quick sec. Oh, self.weights. This is self.weights. Wonderful. Let's see if that fixes it.
There's no attribute weights. Wait, so that would be right.
But it would be like a singular weight that would like cause that, huh?
Do self-weight. And then,
Do you
for every
call,
other
do you need to
instance
call
of
init?
weights,
Do you ever
you
call
have to
init
do a
params?
singular self-weight.
Okay.
Because you're referencing.
Do you ever call
I
init
see.
params in the
Peculiar. Is this all weights? I thought.
so in predict?
It's gonna work beautifully, I swear.
What are you calling predict though? What's the transmit? And fit. So with X. Okay, but init param should be setting weights.
Yeah.
Self-taught. Oh, I see. So self-taught. Wait.
Oh, that'll do it. There we go. There we go. Wonderful. So give a hand for Jackson. But yeah, okay. So anyways, this is the map of our data right here. And pretty much as you can see, given more data, our line just sort of like flattens out, meaning that our model's getting better. Because again, more loss means more error. We want to minimize our loss, right? And then from there, let's do a quick data visualization. So let's just run these. And as you can see, this is our original plot scatter right here. And remember that our model is trying to predict a line that sort of splits our model in half. So I guess like in this case, like it's not really like or let's see here. Yeah, so this is what our model predicts our data would be. And then I'm pretty sure there should be a line cutting it. There we go. And this is what our model actually outputs, a line that divides our input into two different classes right here. This is what we just coded right here. And I'm just going to very quickly go through this last bit of this lab, and then we should be good for the night. So for instance, if I wanted to output the accuracy of my model with my training data, the way I would do that would be as so. So I'll create a method here that stores my predictions. I will call another log method, and then I'll call predicts. I'll input my training data. And then I will check for things that lean towards, in this case, the class that is associated with scores that are above 0.5 on our sigmoid. And then I wrote that incorrectly. Should be just X, I think. Oh wait. It is a train wreck here. Okay. X prediction, Y prediction, checks out. And wonderful. Oh wait. I'm mixing up my variables. This is quite a wreck. Oh wait, X training data, not testing data. Okay. There we go. Okay, so all we're saying right here is we apply our prediction function to our training data, and then we're going to compare that with our actual data. And then from there, we can get a scale of how accurate our model is. In this case, our model is 92% accurate. Pretty good, not too shabby. So we can apply this to our test, or that was for our training data. We can apply that for our testing data right here. Let's run it back. So pretty much the exact same code. So I'll just copy and paste that down here. But in this case, I will be applying our testing data instead of our training data. So if we run that, boom, pretty similar level of accuracy from our model right here. But yeah, that is pretty much it for the guided projects. Apologies that I ran a little late, but yeah, you've just built a model that can apply logistic regression, and you can now scale how well it's doing or not. And you can apply this model right here. This is a pretty like bare bones model. You can apply this to like your own projects and stuff and should work. But yeah, that's pretty much it for today's workshop. Thank you all for coming, and hope you all have a wonderful Thanksgiving break wherever you may be going. But yeah, I'm not sure which tab Jackson has slides on, but yes.
No slides.
No slides.
No slides.
We just raw dogging it.
We're just raw dogging.
Yeah, it's beautiful.
So we're pretty much done. Next week, we hope to see you here for our final workshop, which will be an introduction to neural networks. It'll be much shorter than all the other workshops. It's really just, I don't know, maybe 20 minutes of content, and then, we'll stick around if you want to chat with us about AI or anything else. But yeah, thank you all for coming. We really appreciate it.
Yeah,
Thank you.
and look out for dance moms that wouldn't.